Hi, welcome to 7.2 volume, the disk method. So there are two methods. One's the disk method, we'll do that now. The other one in 7.3 is the shell method. We'll be doing that next, in the next section. Okay, so think about a cylinder. Now if you think about a cylinder, you can almost think of it, if it's a solid cylinder, think about a rectangle with a vertical axis about which it rotates, that's spinning around that axis. It spins around and makes a cylinder. So if you can imagine that shape, think of a two-dimensional shape that's rotated around an axis, we can get volume. So we know a formula to find the volume of the shape, the cylinder. How would we find the volume if we did not have a formula? One approach would be a method called the disk method, is what we're going to talk about here. To find the volume, consider how we could construct the cylinder. That's what I just showed you. Think about a shape you'd get if a rod was inserted in the center of the cylinder along the axis of symmetry. If a slice was made from the axis to the edge of the cylinder, the shape would be a rectangle. So that's what we're talking about here. You get that rectangular shape. That's then rotated around. Now consider the rectangle. If you took a rectangle and attached it to a rod and then spun it around, what shape would you see? If you spun it fast enough, you'd see a cylinder. And this is a fairly simplistic version of what we'll explore in this section. The concept is still the same. Using the above technique, we know the volume of a cylinder to be, volume is pi r squared h, where r is the radius and h is the height of the cylinder. That's the volume of a cylinder. Now consider another shape, say a right cone. If we follow the same approach, we might have a triangle here. So this triangle is spun around to get the shape of a cone. We consider the distance from the center of the axis or pole from here to the outer edge to be the radius. So now we'll have a function for the radius. So in this case here, our radius is not a fixed value all the time. It's not always going to be 2 or 3 or something like that. It's going to be changing. We have a function for the radius. Since the radius in this case is not a fixed value. To find the volume in this case, we'll have to express it in terms of the changing radius and integrate to find the volume. This is formally expressed in the following technique. The disk method. To find the volume of a solid of revolution, the disk method uses one of the following. If it's got a horizontal axis of revolution, it's going to be the volume as pi times the radius squared, integrating from a to b, dx. If it's got a vertical, this in terms of y instead, volume is pi times the radius, the integral of the radius squared dy, that's integrating vertically. Where r of x and r of y is the, or r of y is the function that describes the radius. So let's do an example here. This is why we call it the disk method. So in this shape, we've got a shape set up for us. It's y equals the square root of x. So this is kind of a slight curve to this. This is not a line. It's kind of somewhat of a curve to it. And imagine this being spun about the x-axis. You have that kind of a shape, three-dimensional shape. And we call this the disk method because if you took a slice of this, you're going to have a disk that's going across from, in this case, 1 to 4. We want to find the area of the disk going that height. That gives us the volume. So it's the cross-sectional area times the height. So that's a changing area, and then hence we have to integrate. So our volume is going to be pi times the integral from 1 to 4, from 1 to 4 of the radius. This radius, the radius of this disk is going to be square root of x. So square root of x squared dx. So the volume is going to be pi integral from 1 to 4 of x dx. So pi times x squared over 2 from 1 to 4. So it's pi times 16 over 2 minus 9 over 2. Or sorry, 1 over 2. So that's going to be 15 pi over 2 is the volume of this shape. That's the volume of this shape here. Let's try another one of these. Set up and evaluate the integral that gives the volume of the solid formed by revolving the region about the y-axis. Now, I'll be honest, going about the y-axis is a little different for us. We're not used to going about the y-axis. We usually do x-axis. So we need to think about this. I don't want to call it height. Think of it as width. And the width is more of an x thing. So we've got to solve this for x. So we have y equals the square root of 16 minus x squared. Y squared equals 16 minus x squared. And we can subtract 16 from both sides. Y squared minus 16, equals negative x squared. And then 16 minus y squared equals x squared. So that x equals plus or minus the square root of 16 minus y squared. We're dealing with positive values for x, so we'll just go with x equals the square root of 16 minus y squared. So this shape is going to go around the y-axis. Not quite symmetrical, but you get the idea, I hope. So imagine this as a disk here. We need to get the radius of that disk. The radius is going to be this function, x equals the square root of 16 minus y squared. So our volume is going to be pi times the integral from 0 to 4 of the square root of 16 minus y squared squared. This is the radius, pi r squared. Radius is 16 minus square root of 16 minus y squared dy. So the volume is going to be pi times the integral from 0 to 4. If you square that, you just get 16 minus y squared. Pi times 16y minus y cubed over 3 from 0 to 4. That's going to be pi times 16 times 4, 64, minus 4 cubed over 3 minus the 0. So maybe I should back up and call this 16 times 4. That's going to be pi times 64 minus 64 thirds. That's pi times, let's see, 64 times 3 is, I want to say 192. And that's going to come out to be pi times 128 over 3. So it's 128 pi over 3. Okay, and that is the volume of this shape. So again, we have this disk, think of it going from down here up to there. This disk, and we have to integrate from 0 to 4 because it's a changing cross-sectional area. Okay. Again, feel free to pause if you like. We're going to scroll up. The washer method is another technique. It's a take on this disk method. So a disk is like a solid part. Disk would be solid. A washer would have a hole in the middle. Washers, you know, for nuts and bolts. In the event that the shape is not solid, say it has a hole like a donut, we can modify the disk method and use a technique called the washer method. If capital R is the outer radius and little r is the inner radius, the volume can be found by pi times the integral from a to b of capital R x squared minus little r x squared dx. So let me just draw a picture of that. So you spun this around like a ball, it's hollow in the middle. And here's the center part. I should probably do that in dashed. Be like an empty ball inside this ball. And now this is for horizontal orientation or rotation. For vertical rotation, it's going to be volume equals pi times the integral from a to b of capital R of y squared minus little r of y squared dy. Okay, so just changing the x's, replace them with y's. Okay, let's go on to the next page. Page 4. So here we're going to find the volume. We have 4 different parts to this. Find the volume of the solid generated by revolving the region bounded by the graphs of the equations about the given lines. Y equals 2x squared, y equals 0, and x equals 2. Let's get a basic idea of the shape. Okay, so have is a parabola. And it's bounded by x equals 2 as a vertical line. So we know that this up here is 4. No, 2 squared is 4. This is 8. 2 times 8. 2 times 4 is 8. That's our cross area. So we have different things happening. In one case, it's going around the y-axis. So in this case here, our shape is going about the y-axis. Okay. So what is our radius going to look like? So in this one, the outer radius, a lot of people get this one wrong. The outer radius is distance from the pole to the outside here. That's just the line x equals 2. So that would be x equals 2. In here, what's this one? That's going to be a little more work. We know y equals 2x squared, so y over 2 equals x squared, or x equals plus or minus the square root of y over 2. This inner curve in terms of y, because it's going around the y-axis, would be x equals the square root of y. Now you can't really read that there. X equals the square root of y over 2. So our capital R of y, in this case, is 2, and little r of y is the square root of y over 2. So our volume is going to be pi times the integral from 0 to 8, 0 to 8, 8 as we discussed over there, of 2 squared minus the square root of y over 2 squared. So that's going to be pi times the integral from 0 to 8 of 4 minus y over 2. This is a 4, not a y. That's going to be pi times what? 4y minus y squared over 4 from 0 to 8. So 4 times y is 32. Y squared is 64 over 4 is 16. And I get 16 pi. So that is rotating about the y-axis. In our second case, we're going to go about the x-axis. So let's draw our specific shape again. Draw a little differently. It's looking like that. It's going to go about the x-axis. So imagine this coming down here. Looks kind of like this. Kind of like one of those the players from, I think it's Sorry, or I think it's Sorry Not Trouble. Okay, so one of those, or Hershey's Kiss. Looks like a Hershey's Kiss. So what is this shape going to look like? What is the radius? Well, this one does not have a hole in it, so we'll just go with r of x. Our volume is pi times the integral from 0 to 2 of, what is the function defined? 2x squared. So 2x squared squared dx. So it's pi times the integral from 0 to 2 of 4x to the 4th from 0 to 2. No, Jeff, getting ahead of myself. Dx, got to integrate this first. So it's pi times what? 4x to the 5th over 5 from 0 to 2. So that's going to be pi times 4 times 2. The 5th is 32. 4 times 32 is 128. Minus 0. So it's going to be 128 pi over 5. That's part 2. So I'm going to need to scroll this. Feel free to pause. I'm going to do C is the line y equals 8, and then D will be the line x equals 2. These were chosen specifically for their locations with respect to this shape. Now, when we look at the one line y equals 8, what do we have? This is the line y equals 8 to the top of the shape. So that means the shape's going to be going around that. Kind of like that. And then we have, this is dashed here. That's it. Okay, so that's kind of like a bowl shape. Well then, this has also got a horizontal rotation. And this is y. Y is a horizontal line, just like the x-axis. So here's our rotation. Let's see. We have a big rectangle and we have a little rectangle. Big distance is still, our capital R of x is going to be 8 in this case. What's little r of x going to be? We know this curve is defined to be 2x squared. Wouldn't say it's 2x squared as this distance, though. The distance overall is 8, and we're taking away this 2x squared. So here where 2x squared is small, it's the whole distance. Here where 2x squared is bigger, there's less distance. So it's going to be 8 minus 2x squared. So our volume is pi times the integral from 0 to 2 still, 0 to 2, of 8 squared minus quantity 8 minus 2x squared squared dx. And This part here is where people who are not strong in their algebra skills will tend to have a problem. This is a binomial that must be expanded. So this is pi times the integral from 0 to 2, excuse me, of 64 minus, now this is going to be right here, 64, 2 times 8 is 16, times 2 is 32, that's double negative, so plus 32x squared. And then negative 2x squared is going to be 4x to the fourth, and put a negative there. Okay, so we have 64's go away. And then it's 32x squared minus 4x to the fourth dx. Come down here. Pi times what? 32x cubed over 3 minus 4x to the fifth over 5 from 0 to 2. So it's pi times what? Put the 2 in here. 32 times 2 cubed is 8. 32 times 8 is, I think it's 256 over 3. Minus 32 to the fifth power, 32 to the fifth power is 32. 4 times that is 128 over 5 minus 0. And that's going to be 896 over 15 pi. The last one, we have the same shape, this time, same beginning shape. This time it's going to be rotated around the vertical line, x equals 2. So it's going to be going around this. So what's the shape going to be? What's this, or I should say this cross-sectional area, what's that radius going to be? That's the real tricky one here, the radius. We go from being a full 2 down to being nothing. So if I said it was going to be the square root, and I forgot what we had there before, the square root of, what do I have over there? Y over 2. Well, that's not going to quite be right because whenever here y is 0, it should be a 0, but it denotes the whole thing. This is actually 2 minus the square root of y over 2. So we have the integral from 0 to 8 of 2 minus the square root of y over 2 squared dy. So this is a little more complicated integral. Integral from 0 to 2 of 4 minus 4 times the square root of y over 2 plus y over 2 dy. I forgot my pi. So the volume is going to be pi times what? It's 4y minus 4 over the square root of 2 times y cubed over, sorry, y to the 3 halves over 3 halves plus y squared over 4 from 0 to 8. This should be an 8 here. That's going to be pi times, put all 8s in there for y's, 4 times 8 minus 4 divided by the square root of 2, that's just 2 root 2, isn't it? Times 2/3 from here. That's going to be 8 to the 2/3, or 3 halves, plus 8 squared over 4 minus 0. And we get from that 16 pi over 3. So we have 4 different problems based on the same initial shape. Different rotations. Okay, let's go ahead and go on to the next page.